gentlemen, boys and girls, and welcome to the Very Big Science Show. We're on a very small budget, so we have to make our own sound effects. What I would like to tell you is that normally Scifest happens in person. Normally we would be in Grahamstown right now celebrating Scifest, but due to the pandemic, we've had to innovate a little. And of course, the 25th Science Festival started in October of last year and will end with this science show, March 2022. So we are so delighted to have you all. I can let you into a little secret. Just between you and I, we have got some international and some local acts, and not just any acts. Let me tell you, these are a host of some of the firm favorites from Scifests of yesteryear. For those of you that have ever attended a Scifest, you might have seen some of these performers, these scientists, these science communicators, and loved their shows. And now you get to enjoy it in the comfort of your own home. Well, I'm not going to keep you for too long. I want to introduce you to the first performer. And of course, I'm calling everyone performers because we are actually performing real science and maths in front of your eyes. So without further ado, I would like to introduce Dr. Tanya Reinhardt, all the way from the University of KwaZulu-Natal, and she is going to be talking about glow sticks. You know, those things that you light up at the parties and run around? A really cool thing to do is to glue them to your body, switch the lights off, and make it look like a little bit of a skeleton. Well, I would like to learn more about glow sticks, so I'm going to hand over to you, Dr. Tanya Reinhardt. Take it from here.
Hello, South Africa, and hello, my friends from Scifest. I'm so happy to be here and to celebrate 25 years of your wonderful Scifest Africa. I've been an avid contributor at Scifest Africa. Some of you might know me from workshops and from the sunset shows that I'm usually doing when I'm at Scifest. So today I thought, okay, we want to celebrate, and we're gonna celebrate, of course, in style, and I brought some party equipment with me, and I also brought some audience with me. We have Sonali here, and Sonali is gonna do the light on, light off part, and we have Smanga behind the camera. Hi Smanga, how are you? Okay, so let's start. So I brought these ones with me, and I'm pretty sure most of you already know what I'm showing here. These ones are glow sticks. So and what they should do is they should glow in the dark, and we're gonna be ready, and I want to show you how they glow in the dark. And 3, 2, 1, and whoopsie daisy. There's so much glowing going on here. Okay. Now I'm a bit puzzled. Maybe Sonali can help me. Sonali, do you know why are they actually not glowing? I mean, hello, they do have, do they need some switch or?
I think you should snap them.
Oh, I should snap them. Okay, maybe you want to help me. Quickly here. So snap, we're gonna snap these ones here. Okay, we're gonna snap this one here. Okay, and I can already see there's something happening here. There's something happening here. Okay, right, and what I'm going to do is I'm also going to start shaking them a bit, and maybe we can switch off the lights, and maybe we can see now. Yes, now this looks like a real party effect. Now they finally start glowing. Fantastic. Can we have the lights on, please? Thank you. Okay, so now they start glowing. So by snapping these glow sticks, something happened. So I don't know, you probably won't feel it, but I felt it when I was kind of bending them. I felt like I heard like a little crackling sound, as if something was breaking inside. And this is exactly the secret behind why your glow sticks won't glow from the beginning. So you in fact have two chemicals inside here. So a fluorescent dye And inside this fluorescent dye there is a glass capsule which contains hydrogen peroxide. And only once they are in contact with one another, then you get a chemical reaction, and this chemical reaction produces light. So I thought I'm gonna do an experiment with these ones here. And if you want to try it out at home, please do so. So what I've got here is, I've got some ice cold water, and I've got some hot water, freshly made. If you do it at home, please do not use boiling water, because first of all you might burn yourself, and secondly the plastic might actually kind of melt or deform, and it makes a huge mess. So what I'm going to do now is I'm going to put 3 of my glow sticks into the hot water, 3 of my glow sticks into the cold water. So what do you think is going to happen? Will it change? Maybe nothing's happening? Maybe one glow stick or one side will glow brighter, maybe one side will glow dimmer. So let's try out. So I'm going to put them in, and if we can have the so here we can see the glow sticks, and maybe you've already seen, if I'm going to take them out, you see the ones that were in the cold water, here at the bottom, they are in fact darker, and the ones in the hot water, here at the bottom, they glow brighter. So let's try and reverse them. So I'm going to put now the glow sticks that were in the hot water into the cold water, and the glow sticks that were in the cold water into the hot water. And let's see what's going to happen now. Okay, maybe we just need some time. And I already start seeing that the glow sticks that are in the hot water, again, the bottom half burns brighter. And here again, the bottom half that was in the ice water doesn't glow as bright. If I can have the lights on, please. Okay, so what is actually happening? So what we have here is a chemical reaction. So we have 2 chemicals, a fluorescent dye mixing with your hydrogen peroxide, and they form some other chemicals and they produce light. So when I have my glow sticks in the cold water, what is happening is that you have your chemical A reacts with chemical B to make another chemical, and it produces some light. So a very slow process. And here, where we have the hot water, we have chemical A plus chemical B gives you chemical C plus light, light. So you produce way more light in a much shorter time. So Dani, can I just ask you a question? Do you think that, the glow sticks will last forever?
No.
Oh, fantastic. So no. Do you know why?
No.
Okay, so maybe let me explain. Okay, so the reason is once one of these chemicals is used up, then unfortunately your glow sticks won't glow any longer. But, if you want to keep your glow sticks for longer, you put them in ice water or in the ice tray of your fridge, and then they last longer, but of course you won't be able to see because they're inside the fridge. If you want to have them glow brighter, like party style, then you just put them in hot water, they shine brightly, but the time it will glow or will continue glowing is fairly short. And you can try this out, you can make it an experiment at home. So, thank you so much for watching, and I hope to see you all back in live, back at Scifest, hopefully next year. And if we can just wave it off, and I'll just wave, and happy birthday, Scifest!
Thank you, Tanya. I'm so delighted that you were able to share your knowledge and expertise on glow sticks. And now we also are in for a wonderful treat. We're going to have the team from the Cape Town Science Centre that are going to wow you with some awesome science experiments. Cape Town Science Centre, over to you.
Hi guys, welcome to the Cape Town Science Centre Science Show demonstration. My name is Jamie and today I'll be taking you guys through a simple reverse redox reaction, also known as the chemical traffic light. For this experiment, I'll be using a few chemicals and a bit of water. I'll be using some glucose, so over here I've measured out 7.5 grams of glucose, some sodium hydroxide flakes, over here I've measured out 3.5 grams, and lastly just a little bit of indigo carmine powder, okay, which will be our indicator in this experiment. So for our first step, we are going to be adding our glucose into our water. So I'm just going to move my chemicals out of the way, and that will also create some more space for us to work. So so we're going to start with the glucose first. So I'm just going to move the sodium hydroxide things out of the way, and we're going to be focusing on the glucose. So firstly, it is the dry glucose powder into the water. And we want to get this mixed throughout and making sure that the glucose is all dissolved within the water. So I'm just going to give that a little bit of a stir so that you guys can see that as well. So we've got our glucose dissolved. Next step is also to add our indicator, which in this case is our indigo carmine powder. So that would be this powder over here. And I'm only going to add a little sprinkle into the glucose. This will ensure that the glucose then turns dark blue. So you guys can see how that looks. So I'm just going to take a very little indigo carmine powder, and I'm just going to sprinkle that lightly into my glucose solution. Okay, I think we've got enough. I'll add some more if we need to at a later stage. Let's see what that looks like. So I'm just going to swirl that and mix it through. Okay, that looks like a good blue color. If you guys can see, it's pretty dark, but it will lighten up as we go along. So I'm going to move my glucose now over to the side, and we're going to make our sodium hydroxide solution. So for that, I'm going to add my sodium hydroxide chips into the beaker. And because we are using the flakes and we also want it to dissolve nicely, I'm going to add a little bit of boiling water to the sodium hydroxide, and this will help it dissolve faster. Okay, just to help it dissolve, I'm going to give it a little swirl, as you guys can see. And once all of these chips dissolve, we can then add the remainder of the water. Okay, so I've mixed that through, making sure that they're all dissolved. And now I'm going to add the rest of this water into the sodium hydroxide solution. Right, now we've got two solutions over here. That would be our glucose solution that also has our indicator, and our sodium hydroxide solution, which is our base in this case. Right, so to this I'm going to be adding it into our 1000 milliliter conical flask. And I also need a little rubber stopper as well as a funnel in order to do so. So I'm going to place the funnel on the top over there, and I'm just going to add firstly my glucose solution right into our conical flask. There we go. And then I'm going to add in the sodium hydroxide solution. And once I add the solution, the color should change. The indicator should now show up as a green color. Okay, knowing that the blue is very dark, the green will also be quite dark as well. So let's see what that looks like. Okay, and there, as you guys can see, we've got a green liquid in here now, and this is basically what our solution should look like at this stage. So we are going to leave our traffic light, our chemical traffic light, open for about 5 minutes, and thereafter you can close it. Right, after that 5 minutes, the liquid will have turned yellow, and then your traffic light is ready to use. So for that, I have already set up or done this a little bit earlier. So as you can see, the water is a nice bright yellow. And once we shake it or swirl it, we actually introduce oxygen into the solution, and that oxygen allows our indicator, the indigo carmine, to then oxidize, and that shows that color change to red. And if you shake it a little bit more, giving more oxygen, it then turns green. Okay, and if we let this stand for a while, the glucose in the solution will begin to reduce the indicator, causing the color change to change back to yellow. So as you guys can see, as it's standing over here now, it should start to turn orange as it moves to red and then to yellow. And this is the chemical traffic light, and as you guys can see, it's a very cool experiment. So if you want to try this, please remember to be safe and follow the procedure. Remember, always question, always wonder.
Thank you, Cape Town Science Centre, for those wonderful experiments. I did hear two keywords, indicator and chips. I love chips, but don't eat these sorts of things. And of course, indicator has got nothing to do with turning left or right. It is a wonderful science term. You know, when you're working out acids and bases, very important that you learn the terminology. And now we're going to go on to Marsha Kalika from the University of KwaZulu-Natal Museum. And she is going to tell us all about the world of learning aids for the life sciences. Marsha, over to you.
Good afternoon to Scifest and the online viewers, and thank you to the KwaZulu-Natal Museum and Scifest for allowing us to participate once again in these online platforms, where we get to share our interest, knowledge, and network with others to promote and advance science. The KwaZulu-Natal Museum is proud to announce our range of innovative and stimulating science teaching aids for the grades 10 to 12 life science learners. The science teaching aids follow the art-science concept that integrates two individual disciplines, namely art and science. The visual teaching aids complement the CAPS life science curriculum using art to illustrate scientific concepts. Learners are able to grasp information through visualization, better solve scientific problems, think analytically, inquire, engage, and participate with a greater level of confidence. They are better equipped with skills in observation, accuracy, memory retention, vocabulary, and spelling. The creation of science teaching aids stimulates thinking, questioning, reasoning, design, and problem solving, allowing the mind to think in a logical and systematic way, promoting research, precision, and creativity. The COVID-19 pandemic created an imbalance in knowledge transfer, with the lockdown resulting in lost classroom time and a lack of resources to schools, educators, and learners, creating this huge gap between those that had and those who were supposedly left behind. COVID-19, however, gave us the break we needed. It created an opportunity in the midst of turmoil and uncertainty as educators and learners were in desperate need of life science resources. The demand for support gave rise to the collaborative effort between the KwaZulu-Natal Museum and the KwaZulu-Natal Department of Education to develop life science support materials for difficult topics within the curriculum. Most of the teaching aids were constructed from repurposed or recyclable materials, with the first batch reaching over 3,000 learners within KwaZulu-Natal. The teaching aids were received with excitement from schools and learners alike. And over time, due to demand, it has flourished and embedded itself as part of outreach under the umbrella program, EnviroReach. And this program has served thousands of learners by providing subject support whilst promoting and advancing science awareness and careers in science. Over the last year, additional teaching aids have been added and have progressed from simple boards to 3D models, including the dissection of live specimens. This marks the pinnacle of achievement for science in our program. On the boards behind me, we have a range of some of the completed teaching aids that have been in demand. And on the upper left, we start with the mitosis model, which is part of the grade 10 syllabus and is an extremely important topic which requires a good foundational knowledge and an understanding as it leads on to meiosis in grade 12. Each circular board represents a phase in the process of mitosis in animal cells. DNA replication occurs during interphase, and this is where an identical copy of chromosomes takes place. This is followed by prophase, metaphase, anaphase, and telophase. Mitosis is a process that explains how a mother cell divides to produce two new genetically identical daughter cells that not only allow for growth, but asexual reproduction and the replacement of damaged cells that promote healing. Another highlight is the structure of the plant and animal cells for grade 10 that allows learners to compare and contrast differences through observation. These teaching aids allow one to recreate and represent scientific structures that are not visible to the naked eye, thereby increasing comprehension, vocabulary, while stimulating thought and confidence. If we look at the plant and animal cell teaching aids, the colors are striking. We've got the blue and the green and the reds with the oranges, but at the same time, the organelles are in proportion to represent accuracy. So if we compare the visible differences through simple observation, we can see that plant cells have this set structure because of the cell wall, as opposed to the animal cells that have an irregular shape. We can see that plant cells have a large distinguished vacuole, whereas plant cells have a reduced vacuole or they may be absent. Also, another striking difference is the chloroplasts. We know that plant cells have chloroplasts because they are autotrophs. They need to make their own food. And chloroplasts are involved in the process of photosynthesis, unlike animal cells, which are heterotrophic. So we can see that these models are extremely startling, they stand out, and they're extremely useful to the learners because through observation, one can very easily extract the information that they need to. A few of our other science teaching aids that we've created has been the structure of the ribose nucleic acid for RNA. And this is grade 12, where we highlight the sugar phosphate chain with the nitrogenous bases, emphasizing uracil. We've also created the structure of the chloroplast and that of the leaf, as well as the bacterium and the virus. We trust that this video has provided a new approach and a different form of engagement to research. Art science can be used across the spectrum to unlock new types of creativity and is a stimulating and exciting way of teaching science across the curriculum. Science is everywhere we go, and it is in everything we engage in. Bearing this in mind makes it all the more intentional for us to use artistic ways to communicate this organized knowledge. Thank you.
Thank you, Marsha, for enlightening us on the life science learning aids and teaching aids. And of course, we're now moving a little bit further up into Africa. We're going to go all the way to Kenya with my very good friend, Kenneth Monjero, who is there to represent the Fun and Educational Global Network. And let me tell you, as an affiliate member of this network, he is going to be showing you some wonderful stuff. And this is the kind of stuff that he goes into the various schools around Kenya, wowing the students with real science. Enjoy.
Hello, South Africa. I'm so happy to participate in the big show. And here I am, Kenneth Monjero, always referred to as Dr. Fan from Kenya. I am the founder for Children's Science Center Kenya, as well as the president for Fun and Education Global Network. Scifest, we wish you all the best, and let's go and see what I have on my table. I'm going to do something about clouds. Have you ever touched clouds? Oh no. Okay, so this is a demo that I do mostly with schools, and what I just need is a container, and I also need something known as liquid nitrogen. Oh, there you go. Look at that. So this is my liquid nitrogen show. But remember, I'm talking about the clouds. Are you ready? Let's count 1 to 5 and we'll have our wow clouds. Okay, let's go. 1, 2, 3, 4, 5. Oh, wow, look at that. Yay! So that is none other than Dr. Fan doing the cloud show. What is about the clouds? It's all about condensation, evaporation and condensation. But this is a liquid nitrogen show that is showing you about condensation, and this is liquid nitrogen is very cold, and now I've added water, and now that kind of, this is not smoke, but this is just a process of condensation. So I'm so happy to wish Scifest all the best during this time of the big show. And this is my biggest show in the country. I do this with all learners, from the babies, from the toddlers, all the way to university students. And it changes our attitudes, our minds towards science, and helps us love science even more. And the big show is about loving science and also seeing the applications of science. Hongera, South Africa. Hongera, Scifest.
Thank you, Kenneth, my friend, all the way out in Kenya, for that wonderful presentation on clouds and their formation. I certainly know a little bit about clouds because I spend a lot of time with my head in the clouds. And of course, no, but I was paying attention. I promise I was watching everything that you had to say. And now that brings us on to our next performer, my very good friend, Prof. Ryan Blumenthal, who is representing the University of Pretoria. He is a forensic pathologist. That is a very cool profession. He deals with dead bodies. And not only that, he's an expert on lightning. Not the kind of stuff that makes your skin a little bit lighter, all those beams that you shine during a performance. I'm talking those bolts that come right out of the sky and hit you. He is an expert on lightning. And of course, he dabbles with a little bit of magic on the side. And today he's going to chat to us about a very important principle when it comes to forensics. Low cards principle. Well, when you're gambling, I suppose low cards, high cards, I don't know. Has it got anything to do with gambling? Why don't you watch to find out?
My name is Ryan Blumenthal, forensic pathologist. Today, I'm going to share one forensic technique with you. This technique is so powerful that it has even been used by fictional detectives. We are talking Tintin, Inspector Clouseau, Thomas Magnum, Inspector Gadget, you name it, these detectives have used this principle. This principle I use every single day. I eat this principle, sleep this principle, dream this principle. This is a very powerful principle. It works from the microscopic level to the macroscopic level. It works on atomic level to cosmic level. And this principle is Locard's principle, the law of interchange. Locard's principle is as follows. Wherever he steps, whatever he touches, whatever he leaves, even unconsciously, will serve as a silent witness against him. Not only his fingerprints or his footprints, but his hair, the fibers from his clothes, the glass he breaks, the tool marks he leaves, the paint he scratches, the blood or semen he deposits or collects. All of these and more bear mute witness against him. This is evidence that does not forget. It is not confused by the excitement of the moment. It is not absent because human witnesses are. It is factual evidence. Physical evidence cannot be wrong. It cannot perjure itself. it cannot be wholly absent. Only human failure to find it, study it, and understand it can diminish its value. Sometimes an event is so quick that you cannot observe it. You don't know what it is or what it was. Take lightning, for example. If someone is struck by lightning, we will find signs of heat, barotrauma, signs of light injury, signs of electric phenomenon. And therefore we know that lightning must contain these components. It must have a heat component, a light component, a blast wave component, and an electromagnetic component. So what we discovered is we look for traces of lightning on the ground and on the human body or the animal body, and what we find on the human or animal body or the ground tells us about the nature of lightning. As an example, I can walk on the beach and without even entering the ocean, I can tell you what is in the ocean. We do this because what is in the ocean leaves signs of itself on the beach. Every contact leaves a trace. If you go to a scene, you will leave something there or you'll take something with you. This is what we use every single day in forensic pathology. One day my friend bought me 3 rare quails as a gift. I didn't have a place to put them, so I left them in my back garden and I quickly went to the shops to buy a cage for my quails. When I got back, all 3 of my quails were dead. They were killed by my neighbor's cat. I took my 3 dead quails to my neighbor and I said, "Your pet killed my pets." To which the neighbor responded, "How do you know it was my cat that killed your quails?" To which I responded, "Lady, I'm a forensic pathologist. Do not make me swab my quails." Anyway, following day, my quailless life, I went to the university and I was walking around the grass park and I sat down on a bench and I stood up from the bench, and on the posterior aspect of my trousers was present resin. The overhead trees had been leaking resin, which had attached itself to the benches, which attached itself to my trousers. No good deed goes unpunished. The following night I went to a wedding and in walked a guest with glitter makeup. By the end of the wedding, almost everyone had glitter all over their bodies. What do the quails, the wedding guest with the glitter, and the trees have in common? Locard's principle. Every contact leaves a trace. The cat had bit the quails and deposited saliva and DNA on the quails. The wedding guest, the glitter had spread by means of Locard's principle, and the waxy resin from the trees dripped onto the bench and attached itself to my trousers. Locard's principle is dynamic and at play every single day. The entire wildlife tracking and poaching industries have Locard's principle at its core. A really good tracker will be able to tell you everything about the spoor on the ground. For example, they will tell you that there are 10 elephants present, of which 1 is pregnant. Ancient tribes used to be able to identify members of the tribe through their footprints. All of this is Locard's principle. Every contact leaves a trace. The problem is identifying it and interpreting it. This is where it gets exciting. Locard's principle. Every contact leaves a trace. It sounds simple, but it goes very deep. For example, the contact, it depends on the intensity, the duration, and the nature of the contact. Some things may be subtle contacts. Some things may be harder contacts. And for a good detective, you need to pick up what kind of contact was done. So for example, you may leave a fingerprint on something or a partial fingerprint on something. Now the spies have come up with a very clever phenomenon called UV dust. So what happens is you can buy this UV dust and dust it on an envelope, which is invisible in normal light. However, if you touch it, it gets onto your hands, and if you take an ultraviolet light, your hands shine green. So you can catch criminals green-handed. Even infections spread through Locard's principle. You don't just get COVID. You come in contact with someone or an object with COVID. And for this reason, we can tell you that you got COVID from the person next door you in the hospital and not from the pizza delivery boy. So as forensic pathologists, we are looking for evidence. We are looking for trace. What is evidence? Evidence is anything that has shape or size. It could be as large as a house, or it could be as fleeting as an odor. Every contact leaves a trace. As a medical detective, we have to seek out evidence and trace. If you really understand Locard's principle, and I mean really understand Locard's principle, you will have knowledge that not many people have. You won't believe this, but on your eyelashes and eyebrows are present mites. These mites are part of the normal human biology. You do not have to be afraid of these mites. These mites are called demodex, and every single human has their own demodex population. Now, demodex transfers from person to person, and if two people have the same demodex population, that means they came in contact. In fact, every human has their own population of bacteria on their bodies. These are called biomes. So on my hand, I have my own bacterial population. Within my elbow, I have my own bacterial population. And through Locard's principle, I can tell you that this is my phone because my phone has my own biome population on it. So too with my shoe, etc. It has my bacterial population on it, not yours. So in conclusion, how do we as forensic pathologists use Locard's principle? We can tell you what caused an injury. So for example, if I see certain marks on the skin called tramline injuries, I can tell you that this person was hit with a stick or a bendy stick, such as a sjambok, because every contact leaves a trace. So too, if someone stabs a leather jacket, we can tell you that that knife went through that jacket because of the specific shape that that knife leaves on that jacket. Every contact leaves a trace. We can connect the jacket to that knife. So if you open your eyes, you can be a medical detective in your own life. For example, if you have a dog at home, watch the dog hairs, see how they move through the house. If you are having a braai, you'll notice that the smoke will deposit itself on your hair and on your clothing. You will be able to tell someone that they were at a braai, and if you're that good, you'll even be able to tell them what they braaied for dinner. We use Locard's principle to find out who done it.
Thank you, Prof. Blumenthal, for that enlightening talk. Get it? Lightning. And of course, learning about Locard's principle. We're now going to move a little bit closer to you. We're going all the way to Wits with the Bernard Price Institute of Paleontological Research. And let me tell you, Dr. Ian McKay apparently was turned down in The Voice of South Africa. So he's resorted to writing raps. And this is a rap. I don't know if he actually wrote it. I'm just saying he did, because it had a lot about dinosaurs in it, and he knows a lot about dinosaurs. This is a rap about dinosaurs. I hope you enjoy it.
Yo, so you thought you were the first, but you weren't. With your thirst for knowledge, you proved the reverse. You weren't the first, we were here before you when we ruled the earth. The terrible lizards, the dinosaurs from a long time ago. The ruling reptiles that rule. We may look like fools, but we own the gold. For more than 150 million years, it was the survival of the fittest. The fittest survived. We didn't just survive, we thrived. With over 1,000 species that range in size, from chicken to giant, including Tyrannosaurus. Two of the most ferocious predators that ever roamed the earth. Argentinosaurus, 40 meter long, 3-story tall giant. Giant of a beast, beast of a giant. Because we were the best, the mightiest of the mighty, the greatest of the great. We stood the test of time. We were the dinosaurs, terrible lizards from a long time ago. You may not remember our brain, but you remember our wrong. You remember our size, and you remember our wrong. With over 1,000 species preserved in stone, there are lessons yet to be learned from our bones. protecting ourselves with all the plates, pipes, and horns. Simply to foot or gigantic sides. You're swinging a club to protect our lives, sustaining ourselves, eating plants, insects, and fish. Even swallowing stones to digest leaves. But with razor sharp teeth for slicing meat. Many of us warm-blooded with agility and pace, and bright feathers and move with grace. Because we are the dinosaurs, terrible lizards from a long time ago. And we might eat you if we could meet you, but we can't cause we're extinct. Yes, we're extinct. Cause we're extinct. Yes, we're extinct. Knocked out of the ring.
Knocked out of the ring.
And for the count, a meteor came. Shockwaves and dust, chaos and pain.
Shockwaves and dust, chaos and pain.
Cause we are extinct.
We are extinct.
Forward the flame. Yes, we're extinct. So don't sit grinning in front of your big screen TV, thinking this could never happen to me. For 150 million years, we ruled the game. That was over in a flash when the meteor came. There's still astros in outer space. Climate change, habitat destruction, other species extinction, wars and confliction are some of the issues that you got to manage to minimize the damage. Because we are the dinosaurs, terrible lizards from a long time ago. With over 1,000 species preserved in stone, there are lessons each will be learned from our bones. One last issue we got to resolve. One last thing we got to solve. Next time you eat that finger-licking chicken, remember you are eating a dinosaur. Cause some of us are still alive, yes, some of us still do thrive. One group of us survived the blast. We are the birds, and we are here to last. Because we are the dinosaurs, terrible lizards from a long time ago. With over 1,000 species preserved in stone, there are lessons each will be learned from our bones.
There are lessons each will be learned from our bones. There are lessons each will be learned from our bones.
Thank you, Dr. Ian McKay and the team from the Bernard Price Institute of Paleontological Research for your outstanding rap on dinosaurs. I heard that Dr. McKay actually played a cameo role in that video. He was one of the lyric contributors. You thought I was going to say, I was not going to say dinosaur. No, I do want to say that, of course, Grammy Awards, you better watch out because we have local rapping talent and they are coming your way. And now for our next performer or speaker or presenter or science communicator, all the way out from the UK, from Science Made Simple, we have Dr. Wendy Sadler. And let me tell you, Dr. Sadler is incredibly talented when it comes to making science exciting. She has come to a couple of our Scifest before out in Makanda, and we are always blessed to have her there. And today she's going to be talking about wine and sound. And if you have young kids, you will know all about wine and sound because that's all they ever do. They make that big sound when they whine, but that's okay. You're going to learn about the science behind it. Over to you, Wendy.
Hello, Scifest. I wish we could all be together to celebrate this 25-year anniversary. That's such an achievement. And it's been one of the highlights, I guess, of my science communication life that I've been able to be involved in Scifest Africa over the years. And I've absolutely loved every single visit and every single collaboration that has been done. I was last there in 2016, I think, doing the 20th anniversary. But today I want to show you one of my favourite science demos. So my background's physics and music. I also think we should be raising a toast to Scifest. So I thought we'd put the two things together and do a little bit of science in the wine glass. So you may have seen, or you may know that you can make a wine glass vibrate and sing at a certain note. Takes a little bit of practice, but all you need to do is to stick your finger in, get it a little bit wet, and then move it around the glass. Ooh. Okay. It takes a little bit, but then you start to feel it when it's coming. You have to go at just the right speed. Now what's happening, you can't quite see with this camera, is that my finger, because of the friction between my finger and the glass, it's sticking and slipping and sticking and slipping many times a second. And so as we rub it, that friction, that sticking and slipping, creates a little push that makes the wine glass vibrate. Now, it can vibrate in many ways, but if you want that pure sound to happen, you have to be moving your finger at just the right speed, if you like, to match the natural vibrations that the wine glass wants to do. And we call that the natural resonant frequency. So this is a phenomena called resonance, which you may have heard of. It's where an object, depending on its size, wants to vibrate at a certain speed. So your wine glass is going, this gives us a bit of a boring musical instrument. It only plays one note, but the wine glass is creating that note. So my challenge to you is what happens in a moment when I raise a toast to Scifest and drink some of the water, I'm sadly only water, out of the glass. Now I'm going to pause for a moment, or you pause for a moment and just have a think. What do you think will happen to that note? It will change. So the smart answer would be to just say it will change. No, Wendy, that's not enough. I want to know, will it go up or will it go down? So have a think. What's your vote? Do you think it will go up or will it go down? And then we'll try it. Okay, got that note in your head? Got your answer in your head? La. Here we go. To Scifest. Oh, here we go. It goes up. Well done. So half of you, or however many, are sitting there feeling really clever, feeling smug that you got it right. Well done. But I can tell you, if you got it wrong, you're in very good company, because I've done this demo to thousands of people over the years, and even to an international conference of professors of acoustics. And even in that audience, 80% of them got it wrong. And I think there's a very good reason, because you may have been relating it to a similar experiment that you've tried using a plastic water bottle or a Coke bottle or something. So if you blow across the top of a bottle and then you drink liquid out of that bottle, the note does in fact get lower. So you were doing a very good scientific thing if you voted for lower, and if you voted for higher, of course you got it right. So whatever way you voted, well done. So why is it different? Why does it catch people out? Because in this example, the vibration of the glass, which is started by the friction of my finger, and the water together is the thing that is vibrating. So that's what gives us the resonant frequency. In a bottle, when you're blowing across it, you're creating vibrations in the column of air. So as you drink more Coke or more fizzy lemonade or whatever it is, the column of air gets longer. Now, generally with resonance, with this phenomena, the more of something you have, the slower it wants to vibrate, and so the lower the note. So in this case, we got rid of some stuff, therefore we've got less of it, and it vibrates faster, which is a higher note. In the other case, we got rid of something, but the air column actually got longer, so we had more air, and therefore it vibrated slower. Now, just before I go, I'm going to leave you with a challenge then. And I'm going to tell you a little weird thing about this sound. If you were to look at this sound using an oscilloscope, that's just a machine that sort of prints out or visualizes what this sound vibration would look like if you graphed it. You would get something that's called a very pure wave. It's called a sine wave. It's very pure. And there's a weird thing about human hearing is that we're very bad at detecting the direction of very pure sounds like sine waves. We need the messy waves, the higher frequency waves, to actually be able to locate things. So if you really want to annoy someone at your next party or in a restaurant, play this wine glass, but do it underneath the table where no one can see. And everyone in the restaurant will hear the sound, but they'll find it very hard to know where it's coming from. So that's just a weird thing about the sound. Right, my final challenge before we go. So here's the sound again. I'm not going to do this for you because I want you to go away and try it for yourselves. So we know that when we changed the water, the pitch changed. What do you think will happen if we don't drink any water, but instead we go from playing it like this to tipping the glass and playing it on an angle. Okay, might not be what you expect, but go away and do that little bit of science, and then when you've done it, try and work out why, and then show it to someone else. And that's what science communication should all be about: finding something intriguing, showing it to someone else, and enjoying the wonder of discovery. So enjoy your celebrations, and hello here from Wales, or goodbye here from Wales in Cardiff. And I hope one day soon, not too long, we'll be able to all get together to have some more fun with science. Bye.
Wendy, that was absolutely fantastic. And talking about wine, I might need to take a short little break while our next presenter comes along. We have the wonderful local is lekker Dr. Derek Fish, all the way from Richards Bay at the Uni Zulu Science Center. And he is going to be talking about the science of sound. Over to you, Dr. Fish.
Hello to everybody at Scifest. This is Derek Fish from the Uni Zulu Science Center. First off, I want to wish Scifest a very happy 25th birthday. It's a fantastic achievement to come so far. Our Science Center turned 35 last November, and I know how difficult it is to keep a quality project going, so well done. I have many happy memories of Scifest. I presented a music show there many times, a sports show with Graham Walker, and a space show with my teenage daughter. I want to pick up on some of the things from the music show, and perhaps also to follow on from some of the things which my good friend Wendy Sadler talked about with her vibrating wine glass. So Wendy talked about the fact that sound consists of vibrations which travel as waves, and you can see on the screen here the sound waves from my voice. Now if we look at different instruments, for example, if I start with the simplest instrument of all, just a human whistle, and we freeze that, you can see it's an almost perfect sine wave, and just one single frequency is selected there. Now, not all musical instruments are as pure as that. If I play a recorder, have a look at this shape. And there you can see again, not quite such a pure sound as before. And if I try something really rough like the kazoo, we get a really messy sound there. And the shape and size of the waves really depends on how that particular instrument makes its sound. I really enjoy the wind instruments, the instruments that you blow, and these can be divided into three groups. We have those of the flute family, where the vibrations produced by air escaping from a hole. We also have those of the reed family, like the harmonicas and clarinets and saxophones, where there are little reeds inside the instrument which cause it to vibrate. And then finally we have the lip vibrated family, like our beloved vuvuzela, where you create the vibration by going with your lips. So let's start off with the so-called flute family. Here's a very simple piston flute that sounds like this. And you can see a very simple principle, that when the instrument is short, the note is high, and when the instrument gets long, the note goes low. So you can change the length of this instrument and try to play our South African national anthem. Not too good, because of course it's difficult to know exactly where the notes are. It's like playing a trombone or a violin. So to make things easier, we can drill holes at exactly the right places, like in this recorder, and then it's much more easy to play the anthem accurately. And I think you'll all agree that was much better. The one hole you mustn't cover, this one here, which is strangely called the fipple. If you cover that, you get nothing, because there's no vibrations. Now in the flute family, we have a very unusual instrument. This is the nose flute, which you play by blowing into it through your nose, so not to be shared with your friends. You blow out through your nose like this, and then change the shape of your lip, like when you're whistling, to play a tune. And so on. So that is the flute family. Now the next family is the reed family. These instruments are quite expensive, like clarinets and saxophones and so on, but you can make a really cheap oboe out of a drinking straw. If you blow through a straw, there's no vibration, so nothing happens. But if you flatten the end of the straw, take a pair of scissors and cut it to a sharp point, just like that, we've now got two little reeds which can vibrate inside my mouth. And I can make beautiful music just like in an oboe. Now I want you to think about this, because remember we learned that the length of an instrument determines its pitch, whether it is high or low. So let's make this a little bit longer as we can. And then I'm going to cut the straw shorter while I'm playing it. And I want you to think about how that sound is going to change. And I'm sure you could hear how the pitch got higher and higher and higher as that changed. Now in some instruments that reed is in your mouth, like clarinets and oboes and saxophones. In other ones it's actually inside the instrument. So like in the harmonica, when I blow, there are reeds inside which vibrate. You have to remember when to blow and when to suck. And then you can try our national anthem. And then the final lot are instruments which are called lip vibrated, because you have to go with your lips to make that vibration. Now these include all your brass instruments like trumpets and trombones and bugles and so on. These are really simple instruments. To show you how simple, I've made a bugle out of a hose pipe. It's got a proper bugle mouthpiece and a kitchen funnel. And if I blow on this, you can hear I can get quite a good note out of that. Now, of course, in South Africa, the instrument that we use as a weapon of mass distraction is the vuvuzela. Again, if you blow it, not much happens unless you vibrate those lips. And then you get that sound that we tried to use to distract the opposition in the 2010 World Cup. Now, of course, vuvuzelas are banned from many sports venues. This one is quite useful in that you can fold it in half and you could hide it inside your clothing. But I also have here my stealth vuvuzela. Don't be fooled by how small this is. There's a little bit of balloon rubber there, and when you blow through this, that balloon rubber vibrates like this. And you can get quite a lot of sound from that stealth vuvuzela. So next time you hear some music, while you're enjoying the music, think about science as well, because every bit of music depends on the laws of science. Congrats again to Scifest on your anniversary. Well done.
Thank you, Dr. Fish, for that fabulous presentation on science and sound. I know that you are all going to go and get your sticks and cups and saucers and get some acoustics going, and at least now you'll understand the science behind it. Our next presenter, I have heard that he is absolutely adorable. He was rated the third best looking mathematician in the whole of his household, and that came from his mother. Would you believe it? He has a black belt in buffet, and he is going to show you how to have fun with mathematics. Over to Steve Sherman. Hello, everyone, and welcome to the very big science show. We are celebrating the National Science Festival, and I, Steve Sherman from Living Maths, have been asked to put on something a little mathematical. Well, I can tell you these things are a lot easier when you have people joining in, but I thought I could do a demonstration that you can try at home as well with me. And every now and again, you can pause the video to test these things out on your own. So my first question is, if I take a strip of paper and I take some glue and I glue the end of it, and then I simply place the other side like this, so it makes a regular loop. What I want to know from you is, if I cut all the way down the middle until I get back to the other side, what do you expect to find? Now, in maths and science, We call this a hypothesis. We are going to try and guess what we think the outcome will be, and then we have to test the hypothesis. So if you want to, you can pause now, and then we'll see if you were correct. Now that you've unpaused, I'm going to cut all the way down the middle. Let's see what does indeed happen. Some of you are saying 1 or 2 links. Some of you are saying that the links could be intertwined. But guess what? As you predicted, 2 links. And now I have a beautiful set of earrings. There we go. They even suit me. Wonderful. I don't know how long they're going to last, but they do look very pretty. We're going to try that same experiment again, but this time we're going to make one change. I am going to take the paper. I'm going to put them in a loop, but what I'm going to do is one teeny little difference. I'm going to twist the end once. Now that I've twisted it, what will happen when I cut all the way down the middle and get to the other side? Why don't you pause here, think about it, and then test your hypothesis? I'm going to check it out right now. I'm going to cut all the way along here. Here we go. And we're moving around. We're almost halfway. And wow. We get one large ring. Did you expect that? It's a bit surprising for some of us. Now I have the necklace to match. I'm afraid you can't see the necklace. Maybe what I need to do is just change my outfit so that you are able to see my beautiful necklace over here and my earrings. Wonderful. I'm wondering, what would happen if we took that same piece of paper and this time we twist it twice? What do you think we're going to get? Will we get one ring? Will we get 2? Will we get rings linked together? Will they not be linked together? Let's go. 1 twist, 2 twists, and I stick it on. And now I'm going to cut. Oh, sorry, you're going to pause here. And you're going to try and work out what you think is going to happen after 2 twists. And then you can go cut it yourself and check to see if you're correct. I'm assuming you've unpaused, of course. You wouldn't be able to see me talking if you hadn't. And we're moving all the way through to the end. We're almost there. And look at that. We have some bracelets. Isn't that beautiful? I will try to wear my bracelet. It might be easier just to have it on one arm. So now I've got the matching earrings, the necklace, and the bracelet linked together. That's beautiful. But now we're going to step it up a notch. What would happen if I took one piece of paper like this and another strip of paper like this? This time, I'm going to glue them in the middle. You'll see what I mean once I've done it. I'm going to stick them. And what you will see is I have either X marks the spot. It could be a plus sign. We like math, so it's times and plus. And now what I'm going to do is I'm going to take the 1 and I'm going to stick it together without any twists. There we go. No twists for that one. Then I'm going to take the other one and I'm going to stick that one with no twists. What do you think is going to happen if I cut along the middle here and the middle here? I'll let you think about it. You can Pause if you want to. Come up with a few theories and then test it. Now that you've unpaused, I'm assuming you're pausing or not, but if you're not, that's okay. I just sound rather silly. I'm going to start cutting to find out what we're going to get. Will it be one loop, two loops? Will the loops be intertwined? Let's find out. And we're coming all the way through to the end. That's one. Hopefully the glue will hold and it's not going to fall to pieces. And, well, that's a bit embarrassing. So far we have a pair of handcuffs. This is a family show. I meant a very long bracelet. Family show. So I'm still not done yet. I still have to cut the other bit. So let's do that quickly. Now some of you are thinking maybe it's going to be 4 circles. Maybe it's going to be just 2 circles. Whew, this could be a very surprising result. And in maths and science, we often have surprising results when we try to predict what's going to happen. And then we perform the experiment. And then all of a sudden, look at that. It was not a loop at all. In fact, it turned out to be a beautiful square. Now that was surprising. I'm still surprised and I knew what was going to happen. Well, I can tell you this. If you are interested, you can try the same experiment again, but this time you take the first one. So you take 2 strips of paper, you stick them together, make the cross. You take the first one and you twist the bottom once towards you. You take the other one and you twist the bottom once away from you. And then you stick them together. And when you cut them, instead of getting a frame, you'll actually get 2 hearts linked together. Sometimes you can even fall in love with mathematics as well. I hope that you enjoyed that exercise. It's often referred to as the Mobius strip. If you want to go look it up, you can use Google. I'm sure all the information will be there on the internet, but go and experiment. What I like to do is when I'm working with students, I draw a table and I put there 1 twist. What do you predict is going to happen? 2 twists. What do you predict is going to happen? 3 twists. What do you predict is going to happen? 4 twists. What do you predict is going to happen? Can you identify a pattern? And then, of course, the finale is when you cut it up and it lands up being a square frame. That is always an amazing ending. And on that note, I hope you enjoy the rest of the very big science show. And congratulations to Scifest for this wonderful celebration. That's me signing out. Thank you, Steve Sherman. Wow, you really are as attractive as they say you are, and so smart. Ha! I was blown away. Probably one of my best performances so far, but I am not allowed to be biased. I have to be an objective presenter, but you were my favorite. Anyway, what I would like to say is that we are now going to bring on the Sci Bono Discovery Center, and they are going to be presenting stuff about liquid nitrogen. Now we're going to go into the depth of liquid nitrogen. That stuff that is so exciting and so cold, but it's going to warm your heart when you see what they get up to.
Hi Scifest, my name is Bongi Letwala and I'm coming to you all the way from Sci Bono Discovery Center in Newtown, Johannesburg. Now we are very happy to be part of the very big science show. So we are bringing to you some cool science experiments where we're going to explore a very cold substance. Now you're probably asking yourself, what cold substance could this be? Let's take a wild guess. Could it be ice? Now ice is fairly cold. It would be very uncomfortable for you to hold ice in your hands for long periods of time. Now could it be dry ice? Dry ice is solid carbon dioxide and the temperature is at -78 degrees Celsius. Now that's very cold. You wouldn't be able to hold it for just a few seconds. However, the substance we're going to be dealing with is even colder than that. Now here I have some balloons, and these balloons are filled up with air and they are at room temperature. Now I can say this because these balloons have been sitting here for quite a while, and the temperature in this room is about 25 degrees Celsius. Also, I have a bucket here. Now let's play a game. How many balloons do you think I can fit in the bucket? Looking at their size, I would assume we can only fit one. Now you can also take a wild guess and see if you will get this correct. So I'm going to put the first balloon into the bucket, and it looks like I'm correct. We can only fit one balloon in there. But now I'm going to try and apply pressure. And usually when we apply pressure to balloons that are blown up, we should expect them to pop. But is the balloon popping? Quite not. Now I'm going to add more balloons and even apply more pressure. But is my balloon popping? No, it's not. But now observe and see what happens. Is the balloon disappearing or is it getting smaller? Now guess what? You can actually add in more balloons. Now here goes the last one. We're going to apply some pressure once again. And as you can see, the balloon is not popping. The balloons I've added before are not popping. Something is happening inside the bucket. Now I'm going to bring the balloons out, and as I bring them out, this will help us figure out what is actually happening inside the bucket.
As I bring out the balloons, you notice that they have changed in size. They did not disappear, but instead they got smaller. Now we have exposed them to our very cold substance called liquid nitrogen. The liquid nitrogen is inside the bucket, and it was able to cool down the balloons, in turn cooling down the air inside the balloons. When we cool air down, it changes, condenses into liquid air, meaning it becomes smaller. So it occupies less space than gaseous air, therefore making the balloons to shrink. When we expose the balloons to room temperature, the liquid air changes back to gaseous air, occupying more space, and thus inflating the balloons back to their initial size.
Liquid nitrogen is a very cold substance. Here at Saibono, we keep it in a special container called a juwa. This container helps us keep the liquid nitrogen as a liquid for longer periods of time. The lid has a very nice insulation. That means this does not let heat in or out. It pretty much serves the same purpose as your flask at home that keeps your coffee hot for longer periods of time. But now, what would happen if we expose liquid nitrogen to a warmer temperature? Here I have a container that is at room temperature, and as I said, the temperature in this room is about 25 degrees Celsius. Now, since liquid nitrogen is about minus 200 degrees Celsius, that means this container is about 225 degrees Celsius hotter than the liquid nitrogen. Now, let's see what happens when we pour this in.
When we pour liquid nitrogen into the container, we notice that the liquid nitrogen starts boiling. Boiling does not mean hot, it simply means the liquid of a substance is changing into a gas. So in this case, liquid nitrogen is boiling cold.
We do not handle liquid nitrogen with our bare hands because it can literally freeze stuff. Now I'm sure you're wondering what would happen if you stick your finger inside liquid nitrogen just for 5 seconds. Now I'm not going to try that out with my finger, but instead I'm going to use this latex glove, which is made of thin rubber. And so it is nice and flexible. Now I'm going to stick that into the liquid nitrogen just for 5 seconds. And this is what will happen to your finger after 5 seconds. However, when it comes to the latex glove, it's actually a different story from your finger. When we expose the latex glove to room temperature, it actually warms up. As it warms up, it is able to go back to its usual state. That won't be the case with your finger because the liquid nitrogen will freeze your skin to your muscle tissue, to your bone, and all that's going to happen is you will lose your finger. So definitely, we do not try this with our bare hands.
Nitrogen occurs naturally as a gas, so it's very normal for us to see liquid nitrogen changing back to a gas. Now, in the air around us, we have different gases. There's nitrogen, which is the most abundant. It makes about 78% of the air that we breathe in. Oxygen is only 21%, argon is 1%, and carbon dioxide is 0.04%. And we also have other trace gases like water vapor. I'm sure you can see the mist coming out of my container. That is not necessarily the nitrogen gas escaping from the liquid, but it's actually water vapor from the air coming in contact with the cold temperature. Now, when we breathe out water vapor. If I try to blow out my breath, you can't see it, but it's water vapor. However, if I try to expose that water vapor to the cold temperature, this is what happens. You get to see a cloud. Now, that was not impressive. You're going to do something more impressive by exposing the liquid nitrogen to a temperature that is way hotter than my breath, and that is going to be water that has been boiling. Now, water boils between 95 to 96 degrees Celsius here in Gauteng due to sea level. And now we're going to see what happens when we mix minus 196 degrees Celsius with 96 degrees Celsius in a few seconds.
All right, ladies and gentlemen, we have come to the impressive part where we're going to be making our big cloud. Now I'm going to pour in our liquid nitrogen. All right, we have our liquid nitrogen in there, and over here I have hot water that has been boiling. Remember, we are going to be mixing hot and cold together. Now, please, most importantly, do not try any of the things that you saw at home or anywhere without adult supervision. Thank you so much for joining us. And for this experiment, please count me down from 3 to 1.
Thank you, Sai Bono, for that chilling experience. And now we're moving all the way to Fort Hare. We're going to the FOST Discovery Center. And I know what you're asking. Is it F-A-S-T as in fast? No, it is F-O-S-S-T. But what does that stand for? It stands for the Forte School of Science and Technology. And they are going to give you a range of scientific demonstrations with the explanations. Sit back and enjoy. Thank you, FOST Discovery Center. We love learning new things about science and chemical reactions. And now we're moving all the way to the USA. We get to hear from our wonderful friend, Dr. Janita Pritchett from Steam Forward USA. And a little birdie on my shoulder tells me that you have some good news recently. Put a ring on it. I'm not saying anything. I just heard some rumors. So congratulations. And we're going to hear about the science of chemical changes. Over to you, Janita.
Hi there, I'm Dr. Janita Pritchett, the founder of Steam Forward Academy. And so I'm so excited to be here with you all today to take you all through some fun, hands-on learning experiments that you can do right from the comfort of your own home. We're gonna step into my kitchen so we can do some fun kitchen chemistry and explore the science that is found all around us. All right, let's get over there. We're back in my kitchen for another fun kitchen chemistry experiment. Now this one that we're doing really isn't kitchen chemistry because we're using some supplies that I purchased from another vendor, but we're gonna be doing it in my kitchen anyways, okay? So because we are using actual chemicals, we're gonna be wearing our real PPE, our personal protective equipment. So I have my lab coat on. Of course, I'll put on my goggles and some gloves. Now, these chemicals that we're using are safe, but it's always great to make sure that you are protecting yourself. So, the chemistry that we're going to be doing today is really helping us to understand what are called chemical changes. Now, anytime you have a chemical change is a process in which something new is being formed. Typically, chemical changes are not reversible, and so we'll be able to observe a number of different signs or indicators that indeed a chemical change has occurred in this quick experiment that we're going to be doing. The experiment we're doing today is called foam gnomes, and the foam that we're going to be making is foam that's found all around you. In fact, if you're sitting down on the couch right now, you're probably sitting on it. Or if you have some tennis shoes on, it's probably there, or even in the insulation in your house, it's probably there as well. The foam that we're going to be creating is called polyurethane foam. And polyurethane foam is made by just mixing two really simple reactants together and creating something new. Let's get started. So what we're gonna need is a cup, a popsicle stick, some food coloring if you wanna add a little razzle dazzle to your foam gnome, and our two reactants, okay? So the first reactant we're gonna be adding is what you can see here. And if you could describe this reactant, you would probably say it's a liquid, it's viscous, meaning it's thick. It is a bit transparent, or translucent, which means I can see through it or light passes through it. And it kind of looks like honey. So I'm just going to pour a small amount here. Now this liquid is what's known as a polyol. Polyols have long series of carbons in the middle and then some oxygen and hydrogen at the end. That carbon in the middle is going to make this very flexible. So if we want soft, squishy foams, we would add more of that component. Now our second reactant that we're going to be adding, you can see here. And again, if you describe this, you might say it's a liquid. It's brown. It also is transparent or translucent. It's less viscous than the first component, and we'll need about the same amount of that compound as well. So again, pour it in. And I'm trying to make sure I add about the same amount of each so that we can observe. Now, when I add that second compound in, you may notice that it actually dropped down to the bottom. And that happened for a couple reasons. Well, one, the reason it dropped down to the bottom is because that isocyanate compound is more dense compared to the polyol. Density is the mass per volume that something has. And so things that are more dense will drop down to the bottom, similar to like how oil and water, the water sits on the bottom because it's more dense, more mass per volume. Also, these two things don't want to be around each other because they have different intermolecular forces. Intermolecular forces are things that determine whether or not they're going to dissolve in one another. Will they make a solution? And we use the chemist's rule of thumb, like dissolves like, to predict that. In this case, these two substances have very different intermolecular forces, and so we see a separation that's created. Now, that isocyanate compound that we added has a ring structure in the middle, and then there is some nitrogen, carbon, and oxygen. Now, that ring structure that's in the middle, that's going to make that material more rigid. It's not going to move as freely as our carbon would, that carbon chain. And so if we want stiffer, harder foams, we would add more of that second component. If we want squishier foams, like what we would sit on, then we would probably add more of that first component. Now, it's been about a minute or so since I added these two things together, and you can see there is a little bit of white stuff that's being formed right at the layer of where these two are meeting. And that white stuff is our foam. However, it's going really, really slow. So what we're going to want to add to this reaction is something that's known as a catalyst. Catalysts are things that are added to a reaction but are not consumed by a reaction in order to help speed it up. Now, a catalyst can be a chemical, another thing that we add to our mixture, or it could be an actual physical force. And in this case, that's going to be me being the catalyst, okay? And that's where my popsicle stick is going to come into play. So again, now you guys can see I do have a bit more of that white stuff being generated. That's our foam, but it's going really, really slow. And so we're going to speed this up a bit. Now, it's at this point before you start stirring that if you want to change the color of your foam, you would want to add a few drops here. And so you don't have to do this part. You would still see a color change occur with or without adding food coloring. But if you want like a fun color, this is where food coloring could be helpful. If you don't add the food coloring, you'll generate like a white colored foam, which is fine. But I want to add a little bit of color because like I said, I'm an artist. I like things to be colorful. So just a few drops into our reaction container. So again, I'm going to hold it up one more time before we get it really going. You can see that white stuff being formed. That's something new being formed. And so that is our foam. So it's time to speed this up. Let's go. Okay, so I'm going to stir about 100 times to really get this reaction going. So I'm stirring, I'm stirring, I'm stirring. Mix it all around. And you can immediately see that it starts to get thicker. Signs of chemical reactions occurring include things like bubbling, fizzing, changes in temperature, texture changes, odors being formed, or perhaps expansion because of some gas being released in this reaction. Perhaps a precipitate is formed, or you may even see a color change. And so you can see we're starting to get a lot thicker material here. Those two little liquids are already starting to show evidence that something new is being formed. So hopefully you guys can see that. And so once it starts growing, I'm going to stop stirring and I'm going to use my popsicle stick to help ensure that it grows up nice and tall. Okay, so I'm just using my stick to guide the foam up. If you could see really closely, you would see that there's these bubbles that are coming out, and that's from gases being released as this new polymer is being created. Okay, and so you can see within just a few quick seconds, we've gone from having two really small amounts of liquid reactants to a product that is now more solid in nature. If you could also feel the cup is so hot. And that's because this is what's called an exothermic reaction, which means heat is being released from this reaction. It's like burning up, all right? So a lot of heat is being released here as this polymer was created. But you can see now we have a solid material. And so within a few minutes, we were able to demonstrate all these different signs that chemical changes were occurring. We saw some bubbling. You may see fizzing whenever you have a chemical change occurring. Changes in temperature and texture. A bit of an odor could be produced, and I could smell a little something coming off of here. The expansion, you saw that foam expand to get really tall. You may see precipitates, which means some solid material being formed, or a color change. So I hope you guys enjoyed learning about chemical changes and watching this really cool, fun foam gnome experiment. I hope I get to join you guys again soon and show you more fun science activities. Have a great day.
Thank you, Dr. Janita, for that incredibly informative session. We loved learning about your story. And of course, one of the highlights was that ice cream cone that it wasn't ice. No, it was not ice cream, but it did look like ice cream. And of course, boys and girls, we don't eat our science experiments. No, no, no. Now we're going to call upon the wonderful people from the Albertina Sisulu Science Center, and they're going to give us a quick presentation on 3D printing. You know that stuff that we're not talking printing flat, we're talking printing up and around and inside and outside. Take a look.
My name is Tony Sakloko. I'm with my colleague Banele Trukota. We are from Albertina Nontsikelelo Sisulu Science Center in Kofimbaba. As we know that technology plays a huge role in our daily lives, it's forever changing and it gives us the freedom to be innovative. So speaking of being innovative, allow me to introduce our exhibit, which is 4IR, the Fourth Industrial Revolution. So what is 4IR? It is the new era of innovation in technology, and some of the 4IR technologies that we have here at our Science Center are virtual reality, robotics, and a 3D printer. But we'll be focusing on a 3D printer. A 3D printer is a printer that creates three-dimensional objects from a digital file using a material called a filament. To create an object, the first thing you do is to read the print file from the local memory card of the 3D printer. And then click on Build. To begin printing, tap on the picture of the selected file. After that, the printer will start creating the object. This process works by laying down thin layers of material in a form of a wax and then fusing the layers together. So basically, a 3D printer creates an object by laying down layer by layer, starting from the base of the selected object up to the top until it finishes off. Designers use 3D printers to quickly create product models and prototypes, but they are increasingly being used to make final products as well. Among the items made with the 3D printer are shoe designs, wax casting for making jewelry, and toys, as you can see, our final product.
Thank you so much, Albertina Sisulu Science Center. We love learning about new things and in particular 3D printing. We're now going to move all the way to Australia, to an old friend of the Science Festival, and that is, of course, none other than Dr. Graham Walker, all the way from the Australian National University, and he is going to wow you with his insane science communication skills. Over to you, Dr. Walker.
I'm Dr. Graham Walker from the Australian National Centre for the Public Awareness of Science. Today we're going to build a marshmallow bazooka out of a soft drink bottle. You want to start by drilling a hole in the bottom. Just be really, really careful. Right in the middle, about a 6mm hole. Okay, that's where we're going to put the flame in. On the other end, we want to drill out this bottle lid. Just get yourself a nice big drill bit. Again, just being really careful to get the hole started off carefully so that the drill bit doesn't slip off. Just take real care with your hands. You might want to throw a pair of gloves on, especially if you don't do a lot of work with drills. All right, so just get that started. Once it's through, you can kind of just ream it out like this. Just take extra care with that step. Let's get that little bit of plastic off, get all that crunchy bits out. It should look like that. Get a piece of pipe, 25mm pressure pipe, and you've got to kind of coax it onto the bottle nice and gently. It should fit nice and snug. All right, that's done. Beautiful little build, great for chemistry teaching. What we're going to do is pop a marshmallow in the end there. Then we're going to inject just the right amount of gas. We can do some really nice maths along with our chemistry to work out that we need 40 mils of butane for this amount of oxygen. So it's a great STEM project. We've got a bit of engineering, some pretty primitive engineering, some lovely maths to calculate that volume, and some beautiful chemistry. So this is fully integrated STEM. Here we go, and a lot of fun. So we want to just inject the butane in the end there. Got our marshmallow in there. And all you need is a little lighter. Just be careful as you wave it around the end. It should ignite nice and quick. There you go. Once that chemical reaction takes place, it makes lots and lots of hot gas. That gas itself is hot, so it expands even more. And that forces our marshmallow out of the end in a lovely physics, chemistry, bit of engineering, beautiful STEM project that you can try with your students, but take care, please.
Thank you, Dr. Walker, for yet another wonderful and entertaining science show. We do know that you love making science accessible for people of all ages, including me. And of course, that means that lots of the stuff that you show can be done at home. So if you are planning to do these things at home, don't forget to wear your goggles. And of course, put on your running shoes, because when you set something on fire, you better run as fast as you can. And now, ladies and gentlemen, boys and girls, our final presenter for today is all the way out in Germany. We have Dr. Sascha Ott from Die Physikanten, and he is going to close out the very big science show with some very cool science experiments. Over to you, Dr. Sascha.
Hello South Africa, hello Makanda, this is Sascha from the Physikanten from Germany. I'm very proud to be part of your very big science show. And I want to show you more than just a science demo. I want to show you a real fight. We will have a fight of fire against water. Who will win? Well, let's try. Here's the fire, here's the water, and 1, 2, 3. Okay, seems that the water has won. But what if we made the fire a little bit bigger? We need a little help, of course. Now I'm heating up that candle. So the wax is melting. It gets warm, it gets hot, and it gets hotter than 400 degrees Celsius, and above that temperature, the wax itself is starting to burn. So the whole candle is in flames now. Do you see that we have a much bigger fire? And now we are starting our fight again. Who will win now? The water or the fire? Okay, let's try. We try in 3, 2, 1. Oh! And the fire is still burning. Obviously, this round is won by the fire. Well, why did the fire win against the water? What we had was a wax explosion. So the water got into the fire and the water turned into steam. And this huge cloud of steam grabbed all the burning wax and took it up. And there is the oxygen around it, and it makes a huge flame. And the fire is burning, and the water is helping to improve the fire. Okay, if we have more fire, of course, we need more water. The water should be stronger now. We have really a lot of water. And now let's see. We have a fire against that water. Will the fire win? Let's see. Oh, okay, fire is losing. But, okay, bigger fire. Not a candle, we take a sparkling candle. Will the sparkling candle win? Let's see. Okay. I think we need a much bigger fire. We have 7 sparkling candles. Let's see what is happening now. 1, 2, 3. And you see, no matter how much water you take, the fire sometimes is stronger. And that's what you should keep in mind. No matter how big the oceans of fake news are, a real burning fire of science will always win. All the best for you. Bye-bye.
Thank you, Dr. Sasha, for that very informative presentation. We all know that some children should never play with matches and lighters, but not Dr. Sasha. That is how he grew up. He blew everything up. He used to be a pyromaniac in his old house. And I can tell you now that the message that he left us with was important. The fake news is the water around, and of course, the truth, the real information will continue to burn. And that's what STEM and STEAM is all about. Real science should prevail and spread around the world, and hopefully we won't have any of that fake news going around. So I hope that you enjoyed this fabulous big science show. No, it was the very big science show. And what a wonderful way to end off this 25th Science Festival. And we hope and pray that when this pandemic is long gone, we'll be back in Grahamstown celebrating science, hands on, minds on, and having all of you come and join us again. Thank you, everyone. I'm Steve Sherman, and I bid you all farewell. Bye-bye.